until now, we've always graphed everything on the Cartesian coordinate system, right? X-axis, y-axis, right? So basically, it looks like what we have over here. It's called either the rectangular coordinate system or the Cartesian coordinate system. And the reason why it's called the rectangular coordinate system is because to get from any point to another point, essentially all you have to do is go horizontally for a little bit and then vertically for a little bit, and you create a rectangle like this, right? And that's fine, and it's very convenient to put things on paper. But when you then convert that to anything that is not rectangular, like for example, our planet, our whole entire universe, right? It's not a rectangle, it's not a box. Well, then this is not very practical for us to do, right? It's more practical for us to be able to map something on a curved surface than on a rectangular surface, right? So think about that for a minute. To get to this point, P, right here, how do I get to that point P? I could either, okay, so you could tell somebody, all right, so go horizontally for so-and-so units, and then go vertically to so-and-so units, and yeah, they go exactly to where that point is. Another way to describe that point, let's look at that here, that same point here. You could tell them, you know what, go out radially, like just go out so many units, okay, 6, 7, 8 units, whatever, okay, now you're here. And then rotate an angle of 50 degrees. So from here, rotate an angle of 50 degrees. And again, you get to exactly that same exact point, right? So on the one hand, you could either give somebody horizontal and vertical distances, which form a rectangle, or you could give them a radial distance. Okay, that's when you just, go outwards so many units, and then rotate through an angle, and you can get to the exact same point, right? Because the purpose is to get to the point. It doesn't matter how you get there. And the purpose is to have a precise way of describing that point. So that is pretty much how the polar coordinate system is organized and defined, right? This also is a two-dimensional coordinate system, but each point is determined by a distance from a fixed point and an angle from a fixed direction. Okay, so distance and an angle, which means our coordinates and our variables are no longer going to be x and y. Now they're going to be r and theta. Okay, so it's no longer y equals blah, blah, blah x. It's now r equals blah, blah, blah theta. Okay, all right, all right. On the rectangular coordinate system, we have an origin, we have an x-axis, we have a y-axis. Here, what we normally refer to as origin is called the pole, and the pole is right here. Okay, that's a point. The polar axis is a ray that extends horizontally from the pole, this way. Polar coordinates are defined as r theta, like we said before. And again, r is distance from the pole, theta is axis, theta is angle from here to your point. Okay, so the one thing that's important here is when you convert mentally from rectangular to polar coordinates, the concept of distance, right, has to change a little bit, because now I'm not talking about, like going, in rectangular dimensions. Now, think about outer space, and you could just go out into any direction radially, right? So think about, you could radially expand in any direction. That's what we're going to talk about here. Okay, so that's what a distance is. Your distance will not become a radial distance. Okay? So we talk about radial distances. Okay, so that means, like, if I have a sphere, here's how you could draw a nice sphere, right? If you have a sphere, a radial distance is you just go out from the center to any point in the sphere. Okay? Okay, now, to graph a given point, first of all, positive value of theta implies counterclockwise notation. We know that from before. If r is positive, p lies on the terminal side of theta. So I rotate, 50 degrees, and if r is, let's say, 7, then I'm right there. Okay? If r is negative, p lies on the opposite ray of the terminal side. What that means is, suppose you start from here, okay, and suppose you rotate 50 degrees, right? Okay, now, if r is 3, you're right here. If r is negative 3, you're on the opposite side. Do you see what I mean? So you go 50 degrees. And now this is your positive ray. If r is positive, you go that way. If r is negative, you go in the opposite direction. This is on Alex. Alex knows.
I tried getting it, so yeah.
Alex is no Miss Malikian, but now you could do it, okay? So, just as rectangular coordinates are graphed on a rectangular grid, here we're going to use a circular or a polar grid, okay, representing the polar plane. Speaking of a polar grid, here we go, okay? What does that remind you of? Where have you seen, like in movies, where do you usually see something like this? Don't say a target. Yes, or say it, that's what I'm, like radar, right? Like, like if it's a war movie or if it's like some sci-fi or whatever, like a missile is hitting Earth or like a comet or something else fake that's flying out in the sky, right? And how does it usually look? You have like a array that's rotating like this, right? So it's like beep, 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 beep. And then, so like that ray is spanning it, right? And then all of a sudden you see the point here, right? And whoops, not there. You see a point here and somebody's like, sir, it's this many, whatever miles away. And then that arm spans one more time. And then when it passes over, now the ray, now the point is here, right? So it's like closer, and then eventually the point will get here and everybody's like freaking out, right? So what's happening? It's moving radially inward. Do you see that? It's moving along the same like radius inward or outward or whatever. Okay, so that's what we're trying to say. All right, so let's graph this one. So we have a radius of 3 and an angle of 4 pi over 3. All right, just like on your Cartesian coordinate system, each block or each square represents 1 unit. Here too, each of these lines will represent 1 unit. So it'll be 1, 2, 3, 4. Sometimes you might need to double up and say, 2, 4, 6, 8, just like on the rectangular coordinate system. So if it has a radius of 3, we're going to go out 1, 2, 3 spaces. Now the angle is 4 pi over 3. It's easier for me to do the angle first. So 4 pi over 3 is here, right? That means my ray is this one, okay? So my point is going to be on that ray somewhere, and I go out 3 spaces, 1, 2, 3, that's where my point is, P. Okay? Now if you draw the point, you don't put the line, just the point. Okay, we're just graphing a point here. All right, the next one is negative 240 degrees. So from the polar axis, we're going to go negative 240. So this is 180, 60 more to here. So negative 240, that's this axis, correct? So that's my terminal, that's my ray, okay? But the radius is negative 2, r is negative 2. So in which direction am I going to go? Downward. Here. -2 here. So that's R. You see that? Okay?
That always got me on that.
Ah. Yeah.
And now it's so easy.
And now it's so easy. Okay, so let's do this illustration. We're going to graph P. So that's at 70 degrees and a radius of 2. 70 and a radius of 2. That's right about there. Okay. And then I have P at 2 and 430. So that's 360 plus another 70. Where does that take me? Same exact point. Because what happened here? 70 plus 360. Well, obviously, that's a full circle. Okay. And then what about that one? -290 degrees? Oh my gosh, same exact point, right? Because here we did 360 minus, oops, the other way around. 70 minus 360, right? So then, so what does that tell you? If you have your theta plus or minus 360, you get to the same point, right? Or theta plus or minus 2 pi. Correct? Okay. What about this one now? 50 degrees and radius of 3. So does that sound about right? Okay. Okay, now the other one is 230 degrees. 230 degrees is somewhere around here, but now it's -3. So where do I go? Opposite direction, right? 1, 2, 3 here. And look at that. That's the same exact point. Well, what did we do here to theta? It's 50 plus what? 50 plus what to get 230? 180, right? So instead of adding 360, I added 180, but what else happened? I made the radius negative. I made R negative. Okay? Here, it's -130. So -130 is right about here. But it's -3, so I go back, oh my gosh, to the same exact point. Right? Well, what happened here? Again, it's -R. And what happened to 50? Minus 180. Right? So what does that tell you? Negative theta, I'm sorry, not negative theta, -R and theta plus or minus 180 is the same point, or theta plus or minus pi. Okay? Here is a summary. Same exact thing as we just said, but you know, I don't like just giving it to you. I like you to come up with stuff yourselves, right? So R and theta will be the same if you have theta plus or minus 360, or you add 180 but switch R to -R. Fabulous. Which brings us here. Here's point S. Let's find 4 different pairs of coordinates that name the same point, but we want to make R remain between negative and positive 360. So what's the first point that we could come up with here? The more obvious one. 2 comma what? 210, right? This point, S. So radius of 2, and it's at 210. Okay? Right? So what's another thing we could do? I can't add 360 because I'll go over my limit, but I could subtract 360, so that'll be what? 230 or 130?
As in 2 and then 30.
Oh, yeah. No. No. Here's what I'm trying to do. I'm trying to subtract 360.
That would be -150.
Negative 150. You see? And then I can subtract 180, right? I could subtract 180 and I would get what? 30. So that's if I subtracted 180. And then you have to make it -2, right? And what else could I do? Plus 180 would give me 210 again. 210 plus 360 from what?
Oh, from 30.
From 30, you could do minus 360, right? What would you get? -2, -330. Right? So here I did 330 minus 360. Okay? So just know, you could do whatever's math, like you could add or subtract 360, no charge. You could add or subtract 180, but make R negative. Okay, from any given point, right? Okay. All right, graphs of polar equations. An equation that's expressed in terms of polar coordinates is called a polar equation. Okay, so for example, R equals 2 sine theta is a polar equation. And somebody from the other class earlier, which I loved, they were like, wait, is that like the y equals mx plus b of the, like polar equations? And, yes, that's what it is. That's the y equals mx plus b, okay? So if you had y equals, let's say, 2x plus 1, right? How do we graph it? Like back when you were, oh, yay high, right? How did you learn how to graph that? We plot points, right? So if x is 0, y is 1. If x is 1, y is 3. If x is -1, what's y? -1. If x is 3, y is 7. And then you plot all of those points, and when you connect them, okay, what shape does that give you? A line. So basically, the graph of this will map out every single coordinate point that will satisfy this equation. Yes? Okay, it's the same thing with polar coordinates. To graph, if I graph r equals 2 sine theta, I've mapped out every single coordinate point r comma theta that satisfies that equation. So for example, right? For example, if I wanted to do r comma theta, if theta is 0, what would r be for that equation? 0. If theta was pi over 2, what would it be? Okay, so if theta is pi, we're back to 0, right? Yes? So, if theta is 0, r is 0. R goes from 0 to 2, back to 0. 0 to 2, back to 0. But in the same time, we've also progressed through 90 degrees of angle. So, 0, 2, back to 0. Okay? Which brings us to an important point. I'm going to pause this for a minute. Back to Cartesian coordinate system. We have, for example, equations that look like this. X equals 2 or y equals -3, right? What does the first one look like when you graph it? X equals 2. Right? I see everybody showing me a vertical line. What about y equals -3? Horizontal line. This is when, only one variable is changing and the other variable is the same. So when x equals 2, no matter what y is, right, x equals 2. So their analogous versions in polar coordinates are r equals a constant, theta equals a constant. So let's think about part A here, right? R is equal to 2.5. Remember, R is the distance. R is a radial distance. And if I talk about a radial distance of 2.5, no matter what theta is, my distance from the pole is always 2.5 units. So let me graph a point 2.5 units away. There. Let me graph another point 2.5 units away. There. Oh, look, I'll do another one. Okay, let's just do another one. Okay, let's just do another one. What shape am I mapping out? A circle. Okay? Right? So, and when you graph one of these, don't do the points, just draw the circle, right? Because we know that's what it is. The next one, theta is pi over 6, 5 pi over 6. So, okay, so when r equals 1 and theta is 5 pi over 6, I'm right there. And then when r equals 3, I'm right there. And when r equals 4, I'm right there. But when r is negative 1, where am I now? At the other end. And at r equals negative 3, I'm right there. So 5 pi over 6 will map out a line through 5 pi over 6. Okay?
So
And it's a line, not a segment. Huh?
You would continue the negative.
You would. Yes. Yes, yes, yes. Because no matter what r is, positive or negative. Okay? This is section 1. It's a little bit shorter than usual because there's actually like a part in section 1 that I removed, and we're going to do it in section 3 because I want to derive it in section 3. Okay, there's nothing's being handed to you. Okay, so this homework will be due tomorrow, which is Tuesday, for G period, right? 417. Now, let's move on to section 2. So section 2 talks about graphs of polar equations, and just like in rectangular coordinates, you have all sorts of, different types of graphs, right? You have square root graphs and parabolas and, cubics and so on and so forth. It's the same here, and they have different form. So to graph these polar equations, it's useful to refer to the graphs of corresponding equations in the Cartesian coordinate plane. Okay? So ultimately, rather than looking at change in y with respect to x, we're going to look at how the radius, right, changes with respect to theta. So as you change the angle, what happens to the radius? How big does it get? How small does it get? That's what we're looking at. Okay, so the first example is circles. I know we did a very basic circle before. Now we're going to do a little bit of the more advanced ones. All right, so these have the form r equals a cosine theta, or this should be r equals a sine theta. Okay, and those produce circle graphs. Okay, what we're going to do first is graph 3 cosine theta in a Cartesian coordinate plane. Okay, all right, when theta equals 0, what's y here? 3. When theta equals half a pi, cosine is 0, right? At pi, negative 3. At pi, 3 pi over 2, cosine is 0. And at 2 pi, cosine is 1, so it'll be 3. Okay, so let's just stop and think about what's happening here. When theta is 0, the graph is farthest from the x-axis, right? It's the farthest. It's got a radius, it's got a distance of 3. Okay? As we approach theta equals, this should be pi over 2. As we approach theta equals pi over 2, the distance between the x-axis and the graph approaches 0. Right? Do you see that? And then the graph gets further away in the opposite direction. Right? So from 3, we approach 0. Then it starts to go far again, but now in the opposite direction. And then eventually it turns back around and goes back to its original maximum at theta equals 2 pi. So now let's fill in this chart here and take a look at exactly what we're looking at. Okay. So at theta equals 0, it's 0. I'm sorry, it's 3. Pi over 2, 0. Pi, negative 3. 3 pi over 2, 0. And then 3 at 2 pi. These we know off the top of our head. Okay. And what's cosine of pi over 3? 1 over 2, right? That means that pi over 3, this is going to be 1.5. Okay? At 2 pi over 3. Okay, so 2 pi over 3, now we're on the left hand. X is negative, so it's negative 1.5. At 4 pi over 3 down here, it's negative 1.5 again. And then at 5 pi over 3, it's 1.5. And the rest of them are 2.6. And 2.6. Right? And you can see, okay, that
Wait, isn't 11 pi over 6 negative 0.6?
11 pi over 6 is on the right hand side. So you can see also that the symmetric point, the half point is at pi, and then as you go back, right, you're going to go through negative 2.6 again, then negative 1.5 again, and 0, and 1.5, and 2.6, and 3. You see that? I need you guys to make these connections here. So if you look more closely still, okay, take a look at this one, pi over 6 and 2.6, well, that's over here, right? So that's the point, pi over 6 and 2.6, right? Pi over 3 and 1.5, that's that point right there. Do you see that? Do you see how everything correlates? Okay. Now, let's do this here. All right, let's go on the polar axis and see what's going to happen. Okay? All right. When theta equals 0, my radius is 3. 1, 2, 3 here. Okay? When theta equals pi over 6, I'm at 2.6. Pi over 3, 1.5. Pi over 2, 0. What shape did I just make? Semicircle, all right? So between 0 and pi over 2, as my angle went from 0 to pi over 2, I made a semicircle. So what happened? My radius went from the maximum to 0, and now it's going to go back to the maximum in the opposite direction, right? So now it's going to go back to the farthest point in the opposite direction. So I'm going to go at 2 pi over 3. 2 pi over 3, it's negative 1.5. So not on this side, but on the opposite side, negative 1.5 here. Okay? At 5 pi over 6, it's not positive 2.6, but negative 2.6. At pi, it's not positive, but negative 3. So I go back here. So look at that. You see that? It went back to its maximum, but in the negative direction this time. Isn't that cool? So first we traversed in the positive, now we traverse in the negative. So from 0 to pi, we made a full circle. Okay, that is circle. And then after that, what's going to happen? So let me do it in blue. 7 pi over 6, it's negative 2 pi over 6. So 7 pi over 6, it's not 2 pi over 6, but negative 2 pi over 6. So it's got to go back. Do you see that? And it's going to traverse the circle one more time. How cool is that? Okay, I'm so much more excited about this than you are. All right, so let's go one more time. 4 pi over 3, right? It's not positive, but negative 1.5, so it's over here. So I'm traversing my circle one more time. So I make 2 circles over the 2 pi.
I'm just listening to the music.
Yeah,
It's not too bad.
no.
Just a little background. A lot of making up stuff. That is important. There's finding in the Torah about that. When they were making cisterns for water and her Mecca, they actually talk about a ratio of 3:1.
So what year would that have been?
What year? That was 2,500 years ago.
Yeah, that makes sense.
Probably 3,000 years ago. Yeah.
That makes sense, yeah. It is though. It is though. Right, so do you see that? So we're gonna traverse 2 circles. Okay, so now, okay, summary of circles, okay. We're gonna understand this, not memorize this, all right? So before I would, not have them understand it as well. But now we're gonna understand it. Okay, here we go. When you have the form A cosine theta, right? Cosine is a maximum at 0. Is that correct? At theta equals 0. So at theta equals 0, cosine is a maximum. So let's say if you have r equals 3 cosine theta, when theta is 0, I'm at r equals 3. Okay? Now, if r equals negative 3 cosine theta, well, when theta equals 0, my radius is going to be negative 3, so on the opposite side. So my entire circle is going to go on the opposite side. Okay? Now, when is sine a maximum? At what angle? Pi over 2. Sine is a maximum at pi over 2, right? So the maximum is going to be over here. So look, the maximum is going to be over here. Okay? So that'll be like 3 sine theta. And if it's negative, then it's just going to move down. Okay? Yes? Okay, now. Or mathing. How much is this distance here? The diameter? 3. What's our A in front? 3. Okay? So that, okay, the diameter is the absolute value of A. Okay? If r equals A cosine theta, it's the absolute value of A. And it's got to be the absolute value because diameter is a distance and you cannot have a negative distance. Okay?
What if you want?
Huh? What if you what?
Exactly what absolute value is. Oh yeah, I got it. Yeah.
Okay. Okay.